Tim Mattson and his wife Pat are here tonight. Tim provided this bio. Yes, you did. It's kind of funny. I love it. So Tim is a PhD scientist in theoretical chemistry, a retired ACA level 5 kayak coach, and a level 3 instructor trainer. After a 45-year career in scientific computing, he now travels the world teaching scientists about programming, computer arithmetic. It gets weirder, guys. Sparse linear algebra over algebraic semi-rings. I don't know. And the bizarre world of pseudo-random numbers. Yes, he is weird. These are his words. Yes, he is weird like water and enjoys all that math and physics stuff. So Tim said he welcomes questions. He can talk to you about questions, maybe clarification questions during the presentation. No, not yet. Not yet, Joseph. So please welcome Tim Mattson.
I'm learning a new one. It's the mix-max generator. And it actually generates the numbers from the solution of a nonlinear dynamic system. It claims to have 10 to the 2047 period, which is unbelievable. All right. But if people want to talk on random number generation, wow, I have a great talk called, no, I won't go there. No. We're kayakers, right? How many people here kayak? Hey! Oh, Pat, you don't kayak anymore? Okay, good. Okay. Well, I just have to say, I'm very impressed, each and every one of you, because you realize you have willingly chosen to come spend your evening learning about mathematics and physics. Yay! We love math and physics. And no, I will not talk about sparse linear algebra over algebraic semi-rings, though it's totally cool. And you know, if Oops wants me back to talk about that kind of stuff, I can come back. All right, I got to pay attention to the time though, because they told me I have to be done in 90 minutes. All right. I know when I have to be done. Okay. So here's the outline. You know, math is fun. Kayaking is basically a physics laboratory, you know, in terms of classical physics and learning, you know, how it all works. You can't do better than from a kayak. And then water is really weird. So a little bit of chemistry. We're going to talk about what makes water so friggin' strange. And then I'm going to talk about the lovely compass. It's wonderful. And then I'll go back on Water is Weird Part 2, and we will probe the very interesting question of what color is water. All right? It's a good question. All right, so let's get started with some math. Now, it's really hard because I have about a 30-slide presentation on the math that we really should ideally know. My wife pointed out to me that probably would not go over well. So I'm going to the minimum. Okay. In science, you really have to describe objects and describe how they move. That's the crux of the matter. And it really comes down to numbers. You know, what numbers am I going to attach to keeping track of these things? And there are two kinds of things that act like numbers we have to think about. One are called scalars. They're a single value. How much does Tim weigh? 260 pounds because I'm really fat. Okay, it's a single number. And when you put the units pounds on there, it completely describes the situation. I'm a fat guy. I'm 260 pounds. But then we have these things called vectors. And vectors have multiple components. Like, for example, if I ask you, how fast is this kayak moving? Well, it's moving 4 knots. Yeah, but, oh, it's moving 4 knots due west. You know, in other words, there's a magnitude and a direction. And so it still acts like a number. It still is describing a physical reality, but it has multiple components, a magnitude and a direction. And of course, we mark it with an arrow. But just think of that arrow as another number. And I can do arithmetic on that number. All right, I can add 2 arrows. How do we do this? How do we add 2 vectors? This is actually really useful. I can take one of the vectors, let's say B, and I'll move its head to A. And by the way, that right there proves that I'm a PowerPoint master because I had the animation to bring it there. Yes.
You moved the tail of B to the head of A.
I moved the tail of B to the head of A. Yes, that's what I did. The tail of A to the head of B. And I would get the same result if I moved the tail of A to the head of B. So it's the operations commute. Stop it, Tim. No. We don't need to get into set theory. Okay, no set theory among friends. All right. So then I draw from the tail of A to the head of B the resultant vector. So I can add vectors this way. Another thing that's really useful with vectors is if I have some vector, I may want to know, well, what component's pulling me down or what component's knocking me over? So sometimes you want to decompose a vector. And so take an arbitrary vector, and I have a vertical axis and a horizontal axis, and I can project the vector onto each one. And so I can say that A and B are the components of, A of V, A of H are the components of vector A. So I can work with vectors, and an awful lot of science cares about direction as well as magnitude. And so this can be very, very important. Okay, so here's an example in a context setting. How many people here have paddled across Rosario Strait before? Oh, wow. Okay, it's a classic part of a San Juan Islands exploration. And it's difficult because there's a friggin' lot of current through there, and you get a huge amount of boat traffic through there. So you had better know what you're doing before you take a group across that. And so you got to plan that. You're the head of the group. You're navigating for the group. How are you going to get them safely across? Here's what you do. Okay, you draw the vector for if you had no current and you went straight across. So assuming I'm at tide point, straight across, I assume my group, because I know the group well, can move at 3 knots. I can take the distance off my nautical chart, and then I can compute how long that would take. Now I look up in my tide atlas, what's the current moving at? Well, let's say it was moving at 2.5 knots. So I could say, great, if I had 2.5 knots for 5/6 of an hour, it would push me that far in the time I took the group across. Add those two vectors, I now know where my group's going to end up. But we want to go through obstruction pass. My group is not going to be real happy with me if we get across and we're way friggin' up there. So what I need to do, just using the mathematics of vectors, I have my triangle. I'm going to see how far do I have to shift it down. So I end up, come on, there. It went too far, so you couldn't see the animation. There we go. See? Yay. So I can slide that triangle down to see how far down I have to take the group before we start crossing. And so then once I get down, and the thing is, when you're paddling and navigating around current, you know if you hug the shore, there's not much current. So you can take your group and hug the shore and just work your way down. And then I know from moving that triangle down that if I get down to that point by that little island there, now I paddle the group straight across and the current will carry us right to obstruction point. So you see, thinking about vectors, and I could do all of this on the nautical chart on my deck. And so this is a big part of navigation is how do you incorporate what the current's going to do to your paddling? Well, it's just vector arithmetic, man. It's easy. It's math. It's fun, right? That's cool. Okay, so I need to say a little bit more about math because this actually is what led to me being, the conversation that led to me being here is this math question. And that is, here's an equation for the power of the wind. Of course, online, the person said the energy of the wind. And I immediately looked at it and said, dude, that's not an energy equation. Can you all see that it's not an energy equation? For an energy equation, that velocity would have to be squared, not cubed. Okay. At any rate, that doesn't matter. And I'm not going to mention the person who did that horrible faux pas But no, what I want to talk about though is most people look at that and go, I think that's a Greek letter, the kind of weird scripty P, and I'm not sure what A is. That V, okay, velocity, I get it. How do we deal with these equations? Let's face it. If you have a group on shore and the wind is blowing at a certain level, do you care about the area of the different people in the group, the area of their bodies presented to the wind? Not really. Not really. It's not a big effect. Do you really care about the density of the air? Not really, but you really care about the velocity. And so I want to point out this is how physicists deal with equations. There's this thing called the proportionality. And we deal with that sideways thing, that sideways square that looks like I got tired of drawing a sideways 8. Okay. And that says that Z is directly proportional to Y. If Y doubles, then Z doubles. And what you really care about is the proportionalities. I don't care about a number of knowing that the power of the wind on me is equal to 1/2 the area times the density of air times the velocity cubed. No, what I care about is that the wind danger, that's the power, is directly proportional to the velocity cubed. So now I'm sitting with my group, it's blowing 20 knots, and I've paddled to this group a whole bunch, and I know they're comfortable in 10 knots. Well, that cubed relation says if I double the wind to 20 knots, it is 8 times more dangerous. So now I have to ask myself, would I take this group out into the wind with an 8-fold greater danger? And the answer is I might. If Pat and I were paddling together, we would go, yeah, at least it's not 30 knots. We would at 20 knots. But I must admit, a large majority of the people I've paddled with, I'd think carefully about that. What? Oh, Jay would join us. I'm sure he would. But I, but the real message I want to leave you with is people so often look at an equation and they see all those terms in that equation and they just shut down. Oh, that's too complicated. I can't think about that. Oh, it's too much to keep track of. But the way we deal with equations is we think, yeah, but what really matters? What really matters to me in the problem I'm solving? And knowing that the danger of the wind is proportional to the cube of the velocity, that's the lesson I need from that equation. Everything else, I don't care, really. I mean, I do because I'm weird, but when you're out on the water with people, you don't care. So I wanted to leave you with that because that's something quite useful. Okay,
Tim?
yeah.
The half, sorry to interrupt, does the half take it to half?
For the case of what we're talking about, the half doesn't matter. So if I wanted a number, because the half doesn't change, the half is a constant. Okay, so it in many ways doesn't matter for our understanding trends. And what I'm trying to say is what you care about are the trends. You care about what is the trend in the danger relative to the velocity of the wind. The 1/2 is only important if I want a final number. If I want to compute a number for what is the power for the wind hitting you right now, then I need the half, I need the density of the air, I need the area of the object, I need all of that. But if you think about it, when you're paddling with a group, you don't care about the number, you just care about comparing different wind levels. And so the half is irrelevant. And that's kind of a big lesson I want to leave you with. Most equations, we ignore everything, but the one thing we care about, what it tells us about trends. Right. Now, let's talk about physics, because you know all the math now, right? Yeah. And there it is. I'll pause just a couple moments, and then you give me some questions. There it is. This is it. Do you all understand that math? If you do, you got it. Okay. I will make these slides available, by the way, to all of the OOPS mail list. So, and the version I give will have extra details. It'll be fun. Okay. So this is it, man. That's great. This is what I graduate. Well, no, upper division undergrad in physics major would understand all of that. Let's not go there. Let's instead talk about my pal, Isaac Newton. Okay. By the way, Isaac Newton apparently was a total asshole. But he's also super genius. Could you imagine being so smart that what you were doing, you couldn't do it because the math didn't exist. So to finish what you wanted to do, you have to create new mathematics. That's what Isaac Newton did. He invented calculus so he could continue to do his physics. So an unpleasant human being who happened to be smarter than any of us. So amazing. So what he did is he formulated 3 laws that describes the essence of classical physics. And what I love about this is these 3 laws are intuitive. And once you're aware of them and think about them, they make perfect sense and you can use them. Okay. The first law defines what a force is. You know, you're sitting in your chair, you're not moving around, your center of gravity isn't. Why? There are no forces acting on you. All the forces equal 0, you stay the same. If I'm going to move you, then I have to apply a force that exceeds everything that's balanced out. Look, it moved. Okay, so force changes how you move. Aristotle got that wrong. Galileo and Newton got it right. Okay, then what is that force? And in a long version of this lecture, where I take 3 times longer going through the math, we derive this equation. Okay, we won't. Okay, the force is proportional to your to the mass of the object you're moving, and it's proportional to how much you're changing its motion. That's the acceleration. So F equals ma, mass times acceleration. Okay, that's the second law of thermodynamics. And the next one is why you all don't fall through to the ground, because you're pushing onto your chair because of your weight, and the chair is equally pushing up on you. Down, up, they balance. Okay, the slogan is for every force there's an equal and opposite reaction. It's another way to think about it. So let's think about this in kayaking. So a kayaker, and notice it's kind of hard to see, notice that kayaker is using a proper paddle. Yeah. So, yes. So at any rate, the kayaker puts the paddle in the water and pushes on the water. The water pushes back, and that kind of puts the paddle in a relatively stable position in the water that I can crank around that paddle with my body to move the kayak. So I put the paddle in the water, I apply a force, so I create a force, F equals ma, off I go, the water pushes back because of Newton's 3rd law, and I start moving the kayak forward as it transmits through my body. Off I go. As I'm pushing through the water, though, I'm pushing water out of the way. So it's pushing back on me, Newton's 3rd law again. Okay? When the force of my pushing, when the force of my pushing balances the force of the water pushing back on me, I get my stable cruising velocity. So we can understand all of it in terms of Newton's 3 laws. And I want to emphasize those 3 laws, coupled with Newton's law of gravitation, which we will skip tonight, I'm sorry. I can come back and we can talk about Newton's law of gravitation because it's how he explained tides. But at any rate, that was all we needed. That was the physics we used to get astronauts to the moon and back. So, I mean, really, it's not a lot of physics. You understand it, right? So you were all deeply knowledgeable of physics now. And I'm not being facetious, actually. There's a lot you now know, but there's one more piece, and I love this. I call it the seesaw principle. I'm fat. I've been fat and heavy my entire life. Okay? So I'm like that big blob right there on the far side. And I want to play with someone who's little. Okay? Well, what's going to happen, of course, is we're not going to have a lot of fun playing. It's just like, oh, look, that might be my wife there going, yeah, this is really fun, Tim. Okay. So what am I going to do so Pat will play with me? I know. I will change the pivot point. Okay. And now she can lift me up. Okay. A rotational force is called a torque. It's a rotational force around a point. And the force of gravity due to the blob times the distance from the pivot point is the torque. So by just shifting that lever arm, making it longer, a light person can lift a heavy person. All right? You've probably seen this before. Who was it? Archimedes, who said, give me a long enough lever arm and I can lift up the world. This is exactly what he was talking about. All right, so that's the lever arm. I love the following photograph. This is the most beautiful forward stroke photograph I've ever seen. Look at that. This is a guy paddling by that had a strobe camera going, boop, 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 strobe light going like that, and they had an open shutter on the camera, and they got this image. What I want you to notice, this is a racer with a beautiful forward stroke. Okay, with a beautiful forward stroke that you work on obsessively because you're a racer, the paddle doesn't move backwards from where you planted. All right? And I've seen this in pictures with myself because I raced kayaks for, I don't know, a dozen years. All right? But it's fascinating. Furthermore, what does the paddle look like here? Lever. It's a lever. It's a torque. When your local kayak instructor working with you on your forward stroke, I used to do a lot of stroke refinement courses at OOPS, a lot of them. I would always emphasize upper hand fixed. This is the forward stroke, not doof. If I do doof, the pivot point's down here. If I do doof, the pivot point's up here. I get a lot more torque onto the water. Okay? When I see my friends, the Greenland paddle, they're like, oh yeah, it's like this and like this. It's like, no! The physics doesn't change just because you're using a Greenland paddle instead of a wing paddle or a Euro paddle. The forward stroke, if you want to have an effective one, and you do, I hope, is because you want that lever arm to be long and effective. But beautiful shot. So this is what you want. And sometimes in really, really still water, you can paddle and you can see from the ripples in the water after you go past that for those of you with a really good stroke, you can strive and do this and you can see it in the water. So that's awesome. But we can use forces to analyze our kayak strokes and really get insight into how we should do things. And yes, I'm an arrogant instructor who believes, I said to do it this way and I know what I was saying, really? Yeah. And Pat's rolling her eyes. It's like, no, calm down, Tim. So, but I want you to think about this. So, my center of gravity, you know, from a distance, you count up the weight of every little piece of me and add it up, its displacement from my center line. You will find a point where all the weight kind of balances. It's called my center of gravity. And you can see if I have that out over the side of the kayak, I'm in trouble. Now, also what I have is the center of buoyancy. And if I add up all the displaced water from the kayak and add that all up and sum it together, the vectors, I have a point through which the buoyant force comes up. If my center of buoyancy is inside my center of gravity, I have a rotational force trying to throw me over. So this is exactly, you know, if you don't want to fall over, get your center of gravity inside the kayak and close to the center of buoyancy. That you can see what I'm doing here. I am sculling with my paddle. Gosh, I have too many builds. I'm sorry. No, you're going the wrong way. There we go. Notice I have the paddle in the water. I'm sculling, so it's coming back and forth in the water. Okay? And that's creating a component of force upward, which is balancing the rotational force taking me over. So that's how the physics tells me how I can sit and stay completely stable like this just fine. But I want you to see another technical nuance of what I'm doing there, because look at the lever arm where my upper hand is. It's tiny. I'm not going to hurt my shoulder. Now, if I put it out here, now I got a long lever arm torquing my shoulder. Bad. So that's why the proper way to do that maneuver is with your arm right up here close. So you can see that by thinking about the forces and drawing the arrows and visualizing all the arrows for how the forces interact, you can learn a lot about the right way to do these strokes. And there is a right way, and there is a wrong way. Yes. Okay. So I want to say a little bit, paying attention to the time here, about forces on the kayak when you're moving. So as the kayak, and I'm going to have to speed up here a little bit, as the kayak's moving through the water, it pushes the water away and creates this pattern of waves. And I assume you've all seen that before when you're paddling on a calm day, how you get these waves. Well, that actually is a lot of energy you're wasting. And energy is conserved. Something's making those waves, and that thing that's making those waves is your kayaking moving through the water, and it's slowing you down. And as you speed up, that force goes up high. And there's this thing called the hull speed. And the hull speed kicks in when the length of the wave across the water equals the waterline length of your boat. To go any faster, you have to climb your own wave. Okay? So that's the hull speed. And the hull speed is up there. I mean, a casual paddler is not going to hit their hull speed. But on the Queen Anne kayak, with a waterline length of 16 feet, the hull speed's 4.5 knots, roughly. No, 5.5 knots. You know, if you have a wing paddle in that kayak, you can get over 5.5 knots. So most people can't, but you can. But there's something else on here I want to mention, because there's another line, the line labeled friction. Friction is proportional to velocity. So the hull speed gets larger and larger as your kayak gets longer and longer and longer. But as the kayak gets longer and longer and longer, the surface area contacting the water goes up and up and up, and the frictional forces actually go up. So if you're not a strong enough paddler to overcome that hull speed, or even to overcome the friction, you actually might be better off and faster in a shorter boat. The idea that longer boats are faster, it's like if you have a powerful enough stroke and the fitness to compensate for the frictional force, yeah, a longer boat's faster. But if not, then maybe a shorter boat. And that's why you really want a boat that's the right length, not necessarily just longer. So it's really cool. But this happens because water is friggin' weird. Because water is sticky. It's weirdly sticky. It has no business being this sticky. The frictional forces are amazing. You know, if we paddled through acetone or carbon tetrachloride, first off, you're asking for cancer, don't do that. But you know, it would be a very different experience because the frictional forces wouldn't be so strong. So let's talk about water. Water breaks the rules. Okay, if we went through and looked at a bunch of molecules of the size of water, water's really, really light. So at that size, a typical molecule would boil above negative 90 degrees Fahrenheit. There should be no liquid water on this planet. And furthermore, contemplate for a moment what ice does. It floats. The solid phase of a liquid should not float. That's just wrong. Okay? That's not the way the universe is supposed to work. But it floats. That's really weird. And since we're made of liquid water, it's kind of a good thing that water is so weird. So let's talk about why water is so weird. And first off, if we think about a little bit of chemistry, water has let's just talk about atoms. An oxygen atom has 8 protons that have a positive charge. The most common form is 8 neutrons, which have a neutral charge. And then it has a cloud of electrons, which balance the number of protons because they're negatively charged. So there's 8 electrons to balance the 8 protons. Does this kind of bring back memories of high school chemistry? Like, didn't you love it? Yeah. Okay, but this is not to scale, because the cool thing is if the nucleus were an apple, the electrons would be a mile or 2 away. Okay, so there's like a lot of empty space. And the quantum physics of how all that works is totally awesome. And I won't say anything more about it. But you form bonds often. There's 2 basic categories of bonds. But I'm going to talk about covalent bonds, which are when 2 atoms come together and they share some of their electrons. So here I have an H2O. Hydrogen has one proton. The most common isotope of hydrogen has one proton. If we had this lecture, the nuclear fusion version, we'd talk about isotopes of hydrogen, but we won't go there. So we have two hydrogens connected to one oxygen, and it gives us H2O. But the thing is, oxygen really is hungry for electrons. And it has to do with the physics and the quantum mechanics of how oxygen works. And in the 3-hour version of this lecture, I go through that. But just trust me, oxygen really is greedy. It wants the electrons. Hydrogen could care less. You know, it's happy not having any electrons at all. The solar wind, you ever hear about that coming off the sun? That's just bare hydrogen nuclei. It's protons. It's really happy without electrons. So what you end up with is the electrons are pulled towards the oxygen. So the two hydrogen atoms are mostly positive. You're mostly seeing that proton. But the oxygen has all these extra electrons. And it's like, oh, goody, I'm so happy, I'm so happy. So it tends to be negative. Okay, and it's unusually strong, this effect. And it creates something weird. This isn't the only molecule that does this in nature, but it's one of the strongest effects of the molecules in nature. It's called a hydrogen bond. And the hydrogen bond says that basically the hydrogen from one water molecule kind of grabs onto the oxygen from the next molecule. And that means water sticks together and it sticks to stuff. It makes water sticky. Not only that, it forms these networks. And therefore that makes water really dense. That's why it stays water and it doesn't turn into a gas. It's the hydrogen bonding. And that's why ice, when that network freezes solid, has all this empty space around it, supported by the hydrogen bonds. That's why ice floats. But you need to appreciate, that's weird. That's just weird. That shouldn't be happening. But thank goodness water is weird, because we'd be in trouble. Now, how many of you navigate the right way? You know what the right way is. Chart and compass. Right? Chart and compass. How many are chart and compass people? Whoa. Okay. You're not GPS people, are you? How many are GPS people? Okay. I'll try. I'll be nice. I will be. Okay. I mean, a lot of people go with the GPS and they say, I don't need a chart. I don't need a compass. I just have this little tiny screen because I live my life around a screen anyway. And I'm happy being a little human clone with my screen. And so when I go kayaking, I'm going to spend my time, I'll set it on my deck. And this is me kayaking because I got my face in a screen. Oh, I can see the blue dot. That's really good. When you kayak with a chart and compass, you're sitting there with your chart and you're like, oh, there's tide point. I think that's tide point. Bring out the compass, check, adjust as you take the variation into account. Oh, yeah, that would be tide point. So now as you're paddling, your eyes are up and around looking at tide point. Did my current estimates work right? Oh, obstruction pass is over there. I should have this bearing to obstruction pass at this point. Bring out the compass, look. The point is your eyes are up. You're engaged with the world. It is better kayaking. So a GPS is a great thing to have in your hatch when you need it because you're in trouble. But you want to use a chart and compass because they're just great. All right, so there we go. That's what I do. Now, compass. Oh, this is fun. I hope you like this. Oh, man. I have to speed up. Okay. All right, here we go. A compass aligns with Earth's magnetic fields. Y'all know that, right? Yeah. And you know, Earth acts like a little bar magnet. And you know that the rotation axis is in a nice fixed stable position, we hope. And the magnetic axis is a little bit off. And that's why you have to do all this variation and conversion between magnetic north and true north. Yeah, this is really easy. You all get it, right? Let me just say it's a little more complicated than that. This is a simulation of the field lines. The blue lines are coming into the Earth. and the orange lines are coming out of the Earth. Now, for those of you who remember your physics classes, whether in high school or college, what do we call the point where the field lines go into the magnet? That's the South Pole, folks. We, by convention, call it a North Pole when it's on Earth. Anywhere else where the field lines come in, we would call a South Pole. But we're going to ignore that for now. But another cool thing, did you know we have 3 different North Poles? Okay, we have the North Pole. Oh, wow. We have the North Pole for the spinning planet, the geographic North Pole. But then we also have the geomagnetic pole. And that's if you're sitting outside, like, a little bit past the moon, and you're looking at Earth. And indeed, from a distance, it does look like a bar magnet with the South Pole at the top of the planet and the North Pole at the bottom shifted a little bit. So that's the geomagnetic pole. But what our compass aligns with is what's called the dip pole. And the dip pole is where the lines go straight into the Earth. So when we talk about the magnetic North Pole that we're tracking with our compass, it's actually the magnetic dip pole. Now, how these magnetic fields form is totally cool. It's awesome. Okay, first off, did you know the Earth's core is the size of the planet Mars? So our core is friggin' huge. And we have an inner core that's solid, mostly iron with some nickel. And then the outer core is liquid. And it's friggin' hot at its edge with the inner core. And it's still hot, but not as hot where it hits the mantle. And we live on the crust, which is on top of the mantle. Because you have that temperature difference, what you have is what's called turbulent convective flow of the iron and other materials going up away. Oh, I'm cooling down. I'm going, oh, I'm heating up again. Oh, I'm cooling. Oh, down I go. So you get these poles. Okay. And because they're so energetic, they've had some of their electrons stripped off. So what do we call a moving charge? That's called current. Think about an electromagnet, folks, right? You take a nail and you wrap a wire around it. Why? Because you're going to take current wrapping it around. What does it do? It turns that nail into an electromagnet, right? You folks ever do that in school, right? Right? So all these coils spinning around, these loops in the convective flow create magnetic fields. Well, the magnetic fields are moving up and along, and because of the spinning Earth, they kind of organize out. So they'll look like this, or these out because of the spinning Earth. Okay, if you have a magnetic field moving up through there, what does a moving magnetic field do? Creates current. Oh dear. so they reinforce each other, and the magnetic field zipping by creates current, which creates a magnetic field, and they self-reinforce, and we get a nice hefty magnetic field. Now, if we look at, and I got to go faster here. Yeah.
Is that what helps create the current?
The current is created by the heat. Because it's iron, it's able to lose some electrons and carry the current. And anything with a charge that's moving creates current. Doesn't matter what it is. It's iron in this case. But it's not because it's iron, it's because it's so hot, it is giving some electrons out and about. So it's moving charge. Where I want to go with this, though, is when you work with a compass, you have to read, and it's way too small to read, I'm sorry, but you have the compass rose with the magnetic compass direction and true, and they're shifted. And that amount of shift is called the variation, right? You know about that, right? Do you know the magnetic dip pole is moving? That the variation's changing? Here I'm showing how it's changed from 1900 to 20, whatever it is. Right? It's changed a lot. And look at the distance it's changed. When the dip pole was first nailed down around 1850, it was down solidly in Canada. 2025, I had to do some extrapolation and scaling to get that last data point. It's well on its way to Siberia. It's already past the geographic North Pole. What's happening? And it's actually accelerating. It's moving about 50 miles or so a year. So it's accelerated. It used to be moving only about 10-ish miles a year. It's now moving about, oh, there's this 30 to 51, 37, right? It's 50 kilometers. Here's what's happening. You have these blobs, and I mean it. When you read in the technical literature, they're called blobs of negative magnetic flux. They're blobs of material that are inhibiting the magnetic fields. And because they're vectors, you're adding up all these vectors to get the overall vector for what you get with the Earth's magnetic field. See why it's handy to know about vectors? They have magnitude and direction. So if I'm adding up and I'm going to weaken some of the other vectors, it's going to change how you add up to get the final resultant pole. And what's happening is the blob over Canada is weakening, the blob over Siberia is strengthening. And that's moving the magnetic pole. What does this mean? Nobody really knows. How much longer will it go on? The models suggest another decade, but we don't know. We friggin' don't know. But I want to tell you something you may not know. Next time you're talking to a magnetic field, thank it. Because if you look at the 3 planets that are in the Goldilocks zone, so this is the area orbiting the sun where, based on solar flux, the planet can support liquid water, and therefore things can live on it. Earth has this massive, powerful magnetic field. And you can see this is an artist's rendition, not to scale, but you can see what it's doing is it's causing the solar radiation to shift around Earth and protect our atmosphere. So that's why we have a stable atmosphere. Mars doesn't. How much atmosphere does Mars have? It was blown out into space by the solar wind. Venus is more complicated. Okay, I'll be done in. Venus is more complicated because what the solar wind did, because Venus doesn't have a magnetic field either, what the solar wind did, though, is blew off the water. That means it couldn't remineralize its CO2. It had a runaway greenhouse effect and boiled its oceans. And as its oceans went into the atmosphere, the sun blew off the water. And now your Venus is so hot that on the surface of the planet, you can melt lead. So be very nice to your magnetic field. If we didn't have a magnetic field, we would not be alive. So thank you, magnetic field. You need to hear that from us more. Okay, so I want to close by talking about a wonderful, wonderful question I have. And that is, what color is water? Okay, there's glasses of water around this room. You look at it, what color is that water? Clear, huh? Well, now here I have Crater Lake, and it looks blue, but it's just reflecting the sky. And then I have this other, I don't know where that picture was taken, but it's green, but that's the algae. So what color is water? Well, let's think about this. There's a lot of words on this slide. Just listen to my voice. So this is something, when I do PowerPoint slides, the goal is to have a briefing document that someone can read them afterwards. I'm losing more. Goodbye, thank you. Okay, because you don't want to miss what color is water. All right. So physics completely reinvented itself starting about 1900. We call it modern physics. And this is a story that takes about an hour to tell. And I have it, I can tell it, but I won't now. But it all started with people taking black metal cubes, hollow, and poking a hole in them and heating them up and seeing the light that comes out. It's called a black body, and the light that comes out is called black body radiation. And you see that line that has very little text, but just keeps shooting up. So that's what the classical theory of light said would happen. That smaller wavelengths would fit more and more and more into space, right? Because a big wavelength, you can't put very many of them because the space is only this big. But little ones, it's like, oh yeah, you can just pack them in there. And so this guy named Max Planck came along, and he noticed that experimentally, you get a peak and then you come down. So the small wavelengths are rare and the long wavelengths are rare. What's going on? Classical theory said it didn't make sense. He said, what if we assume that energy is not continuous, that energy is in fixed blocks that I'll call a quantum? Yeah, energy is quantized. And they said, well, Max, what energy is quantized? It's like, I don't know. I don't know. I'm just looking at the math. And if I look at the entropy and if I look at the thermodynamics and his analysis is brilliant. Is it, if the energy is in units of a fixed number times this constant H. And I don't know if he's the one who coined the phrase, but that constant H is now called Planck's constant. I'm assuming he didn't give it that name. But that's what he said. It's quantized. And if I do that, my theory matches observed. And everyone's like, okay, Max, you solved the problem, but you didn't explain it. Well, then a little patent clerk working in Switzerland one year, and I am not making this up, okay? This year in physics circles is called the miraculous year, literally, or they do it in Latin, annus miraculous, okay? Because he published 4 papers, each one of which was worthy of a Nobel Prize. One of those papers was he explained what Max found. And he said, if I shine light on a piece of metal, at some point, if I go to a short enough wavelength, I'll spit off electrons. But if I have a longer wavelength, no matter how many of them I do, I won't spit any of them off. And that's because the thing that was quantized by Max, his work, was units of light, which I'll call a photon, a particle of light. All right? So this is what made us realize that the wavelength of a light is inversely proportional to its energy. And it completely changed how we thought about light, to the point where people just expect it. Blue light's more energetic. Ultraviolet light will give me a sunburn because it's so energetic, right? But the visible light, we're not going to sunburn off of this because it's not as energetic. For us, it's second nature. I'm going to make it. For us, it's second nature. But this was a radical new discovery. Now, it turns out that it's not just the absorption of light in the visible range, it's all light. And so molecules, their motions are quantized. If they vibrate, like you see the one at the top there going, okay, that takes in usually infrared radiation. And you see the other ones rotating, I can't do that. Okay, that takes a lower energy. And so those motions take lower energies. Okay, I gotta move fast. So if you think about water is a tiny molecule. The wavelengths that can fit around water are really, really tiny. So if you can get any light from water, it's way beyond what we can see. But look at this picture here. There's a little itty bitty glacier in Alaska. What color is it? If you've been around there and the projector's not doing a good of a job, it's a deep blue. And to give you an idea of how big that glacier is, look not far away. That little tiny black dot, you realize that thing is friggin' huge. Kayaking around these glaciers are mind-boggling. And once again, the picture as it comes through the slide doesn't give you that sense of a ghostly blue color that it has. But it's amazing. They're blue. And what's going on? Well, here I'm looking at the wavelength of light and how much is absorbed of water. Okay, so I put it in an instrument and I look, oh, this water coming through. Now, if I go and look at the range of the vibrations of water, there are 3 of them. One is the asymmetric stretching, one is the bending, flapping, the other one is the symmetric stretching. They're all in that range into long wavelength. And if I magnify that by 10, what you see is those vibrational modes are kicked into overdrive and they absorb some red light. And so that's what makes the color of water is blue. And I think you can see it better in this picture, or you can see it even better here, because it turns out it works in Iceland too. The color of water is blue. The color of water is blue because water is friggin' weird. This is the only material in nature where you can see an overtone vibration changing the visible light, but with the naked eye. There's nothing else in the universe that does this but water, because water is weird. And we love weird water, and the color of water is blue. All right, I'm now done. I had to cut so much. If you liked this, yeah, thank you for cutting it. I get that. But for those of you who liked it, let the program coordinators know, because I have a talk about this length about wave physics. And it is awesome. It is awesome. Okay, I'm done. Yes.
I'm gonna train the camera on you.
Well, that's a scary thought.
Somebody from the chat would like to see the motion you were doing for the proper technique of paddling. Yeah.
Sitting in the kayak, rewind, plant the blade like that. The key thing is the upper arm is a fixed pivot point to give me a long lever arm. And the muscles are oomph. Yes, ma'am. Use the term what?
Rotate.
You plant the blade and then rotate. That's for those of you online who didn't catch that, that's my wife, who's also a hardcore kayak instructor. We are a tremendous team, weren't we, Pat? Yeah. For years, we were a big part of kayak education here at OOPS. So, yes. Plant, then rotate. You see a lot of people like, I'm planting while I'm rotating. Oh, that's really nice. No, it's not. But the big thing I was making is the upper arm is fixed in a high pivot point. Yes.
That translates to new pattern also?
Does that translate to what?
New pattern?
Does that translate to canoe paddling as well? I want to emphasize I'm not a canoeist. I've played with canoe paddles, but physics is physics. You still are going to want a long lever arm. But my lovely wife, Pat, knows far, far more about canoe. It translates to canoe paddling. You still want to use the large muscles of your body, and you want a long lever arm, because what you're doing is applying torque to the water. So, yeah. Yes.
What's the difference between friction and resistance?
So friction refers, what's the difference between friction and resistance? Resistance is a more general term. It refers to anything that impedes your motion. Friction is specifically an interaction between materials, one sliding by the other. And it's resisting that motion of one sliding by another. So friction's a very specific type of resistance.
Follow-up, does there have to be touching of some sort for there to be friction?
I'm going to say yes, but only if you let me throw quantum field theory in.
No.
No, okay.
Yes, in general?
Yes, in general. I mean, you can have friction from electromagnetic fields, and then you got photons interacting, and now we're getting into quantum field theory. And trust me, knowing quantum field theory does not help you be a better paddler, so I've left that off the table, which hurts me deeply because I happen to love the subject, but no. Any other questions? None? Okay, so you'll all will remember, water's weird, it's blue, vectors are your friends. Oh, yes.
So, with the stroke,
With what?
with the forward stroke,
Forward stroke again, yes.
or serpentine. But this hand, moving across like this.
So
This is what like the white windshield, technique is favored by, wing patterns.
So the question, yes.
Anyway, the forward stroke, there is, it's not this, there is.
You're wrong. You know, there's a saying that if you're really, really cold and you're in a group of people who are really, really cold and you need to get people fired up and warmed up, just ask them to argue about Inuit paddle forward strokes versus Euro paddle forward strokes. Okay, it gets, boy, do you get people passionate on every side of the issue. I'm right, you're wrong, and the reason is I have physics on my side. The basic physics of how the forces work in a paddle stroke do not change just because you're an Inuit or a Euro paddle. However, there is a lot of juicy detail on this because the thing that the physics at the simple level we're talking about doesn't take into account is biomechanics. And there's absolutely no doubt that the biomechanical smoothness of that Inuit stroke feels really good and people love it and it works really, really well. Okay. It's not as effective as the wing style. The wing style gives you more oomph per body output, but it's not all about racing. You'll never see a racer race with an Inuit paddle. The power of Inuit paddles is how ergonomically friendly they feel. And if you look at my Inuit stroke, it starts like the wing and then finishes out to the side. But the first part of the stroke is front loaded and is very much like the wing paddle. At any rate, as you can gather, I could also come back and give an hour-long talk on Inuit versus Euro paddles versus wing paddles. How many people here have a wing paddle? Whoa. No, wing paddle. Oh, a wing paddle was invented by the Swedes several decades ago. And in cross-section, looks like a spoon that is stretched and twisted into an airfoil. So when you plant the blade, boom, and you slice out, you get a lift component in the forward direction, which makes it stick all the more aggressively. And it adds, they say, about 17% greater efficiency to your stroke. Go ahead, Pat.
So what about how we use? What about how we use?
So most of you probably use Euro paddles with a flat blade. They're more forgiving than a wing paddle. The thing about the wing paddle is if you do the stroke wrong, it rips the paddle out of your hands. And if you don't let go of it when it rips the paddle out of your hands, it will flip you over. So no, so Carl Anderson, I don't know if he's still around these days, brilliant paddle instructor, Carl Anderson. He and I experimented with, you teach someone the basics of the forward stroke, then you give them a wing paddle. Because remember what I just said, the wing paddle, you do it absolutely right, or you're disaster. What we found is students didn't appreciate that. It did not work out well. So I do not give students wing paddles anymore. We're done.
Wow, that was a lot of fun, and holy cow, yeah, physics is hard stuff. So if you have any more questions, Tim's still here. Feel free to corner him, and thank you so much. We'll be back here again in October. Thanks, everybody. Ciao.